Good morning. Welcome to Krishna's class. Now, let me start this talk, and in which we are investigating whether the Fourier transform map from L1 T to C naught is an onto map. Now, you know that the Fourier series, when you construct for a function, there is no guarantee that the series would converge to the function everywhere. This we have already seen. Okay, and in fact, more precisely, we have seen that if f belongs to is a continuous function on T, and then you can write down the Fourier series for that, and you naturally add this is the Fourier series for that, and then you naturally ask whether the Fourier series converges at every point to the value of the function given. Now, this is the question that you are asking. That is, does there exist pointwise convergence everywhere? Now, this question we have settled. Okay, we have seen that the answer is no. The details we have already discussed, so I am not going into that. A similar question we are asking here, but this time slightly different. And what we are asking is the following. We start with L1T. Let us first fix the notation. Now, T denotes the unit circle in C, that is the complex plane. L1T is the notation for the set of all functions, complex valued functions, which are measurable on T with integral from minus pi to pi mod f t dt finite. You know that this class of functions form a linear space over the field C. Now, such functions, because you see it is on the unit circle, if you map it to the real line, or essentially wrapping this real line around the unit circle, then you see that at every point on R you can define a function. A function which has the property that it is periodic with the period 2 pi. So that essentially the function is what it is defined on the interval minus pi to pi, or any interval of length 0 to say a to 2 pi plus a. And then it is extended by periodicity to the whole of R. So we have f is a periodic on R with period 2 pi. Now, you see that the Fourier coefficients f hat n is defined by 1 upon 2 pi integral minus pi to pi f t e to the power minus int dt. In fact, you see that f is equal to, this is what you have, f is equal to, we are trying to write it in the form of a series alpha n e to the power int, where alpha n are just complex numbers. So, is it possible? This is the question. If so, if that is so, then one can evaluate alpha n as because of the orthogonality properties of the e to the power int. Okay, then you can compute alpha n as 1 by 2 pi integral And this is essentially what we designate by f hat for n belonging to Z. So you see that if f is in L1, then this is well defined. This number f hat n is well defined. That's quite easy to see whether the integral exists or not. This is the question that you are asking. And because of this condition, you see that the integral exists. So for every f belonging to L1t, f hat n is well defined. Now L1t is, now you can endow L1t with a norm. It's called the norm 1. Okay, this is the L1 norm you have. So this is defined by norm 1 of f is 1 by 2 pi integral minus pi to pi mod ft dt. Okay, so with, now you look at this L1t with 1. So it is a normed linear space now. What more you can say about this linear space? You can say that it's a complete normed linear space, or in the standard language, it is the Banach space. Okay. Now further, we also know that for every f belonging to L1t, mod f hat n is bounded by norm f, norm 1 of f. That's quite easy to see, because all that you need is just take f hat n. Where is f hat n defined? F hat n is defined. Take the absolute value, and then you see that this is less than or equal to 1 by 2 pi integral minus pi to pi mod ft, because the modulus of this is equal to 1 dt, and that's what you get as f hat n mod f hat n is less than or equal to norm f 1. What does this imply? This implies that f hat n is bounded by the L1 norm of the function f. You see that for every n, this is true. Therefore, you see that for every n, f hat n is determined also. So you can now write a sequence f hat, which is in the form the sequence f hat n for n belonging to Z is called the Fourier coefficients of f, and the corresponding series is this. And the corresponding series f, instead of equal to, because equal to is not a very correct term, that's why it is put, is given by this particular notation. That may not be point wise, it may not be equal. That is why we don't write simply 2. But you have this one. This is called the Fourier series for f belonging to L1. So for every f belonging to L1, Fourier series is defined. More or less, the sequence f hat n is a bounded sequence of complex numbers. Okay, right? So the question that you ask is, can you say more about it? Do you have any further information about it? So we have seen that. So let me just temporarily, we don't need this notation for long. We designate by bounded sequences by the small m. So on this m, So this is the collection of all bounded sequences, which you know is with the usual addition. It's a linear space. Now you see that what we have seen is every f hat, so or f hat is an element of or f hat belongs to M. It's a bounded sequence. Okay, so this is called a bounded sequence, space of bounded sequence. Or let's see this. So at the outset, we immediately get f hat is an element of M for every f belonging to L1T. Okay, can you say more about it? This is the question. So, more deeper properties we have proved already. We have already proved that limit n tending to plus or minus infinity equal to 0. That means this is not only a bounded sequence, but it's also a sequence which converges to 0 in either way, to the left, to the right. Okay, so this is usually designated by C0, small c0. So small c0 you take as the set of all M such that the tail of the sequence in either way goes to 0. It tells a lot of things. It's not only a bounded sequence, it's a convergent sequence, and it converges to 0. Okay, it's not only a convergent sequence, but it converges to 0. So that is the more finer information about the Fourier coefficients for functions belonging to L1. Okay, so that we have proved. Okay. Now it's also, it's not necessary. See, you can look upon this as a map from Z to, see, every sequence is a map from a set of all natural numbers. So this is a two-way sequence. Therefore, this is a map from Z to. So what you have is that C0 can be considered as the set of all functions with compact, the set of all functions defined on Z, okay, which goes to 0 as n tends to plus or minus infinity, and this is the notation for all such functions. So we use the language of functions rather than the sequence here. That is also possible, but that is irrelevant and we don't use it very often here in this analysis. Therefore, we shall not we just made a mention of this for your information. That's all. It's not very relevant for our analysis. Therefore, see, f hat is a map from to Q naught. Okay. The natural question that you ask is what type of map it is. What kind of map is it? Okay. You have already said, see, we are just coming down. So we constructed a sequence out of f hat n. Then we immediately recognize that it's a bounded map. So f hat is bounded. And f hat is a sequence convergent and converging to zero as so we first observe that it's a bounded sequence whenever f is in L1. Then it's much more than that. It's a sequence which is convergent and converges to 0 as n tends to plus or minus infinity. That's something which we have already proved. Now we want to ask more. Therefore, what you have, you know that this f hat n is in what you call standard notation C naught. Okay. Therefore, in general, at the outset, into C naught. Now we ask the question, is this an onto? Is an onto map. What does it mean? You take any sequence, that is, take any sequence Zn of complex numbers such that limit n tending to infinity plus or minus infinity equal to 0, then a function this is what you mean by it's an onto map. Okay. You have seen that the sequence f hat n is an element of C naught. We ask the question, take a sequence in C naught, any arbitrary sequence in C naught. Do you have a function f in L1t with the property that for that function, the corresponding Fourier coefficients turns out to be the given sequence. Okay, so that's the question. Okay, so given, so let me just write this up and then start investigating this. So this is the question. Such that the Fourier coefficients f hat n is equal to Zn. This is the central question that we are going to examine in our lecture. Now we shall state the theorem. Okay. F hat is a one-to-one bounded linear transformation of L1t into C naught, which is not onto. This is the important part. Okay, but in the bargain we also prove that the mapping f to f hat is a one-to-one bounded linear transformation. So let us use that. Bring in the notations required to analyze this problem. Let capital lambda map f to That means capital lambda is a map from hat, which is essentially C naught. So you are taking F from, so every F C naught first thing that you observe is that, because you know that you are working from one linear space, one normed linear space into another normed linear space. Okay, what is the norm on this? So C naught, so norm of Zn you define as the supremum of over n. Okay. So C naught so what we have is this, we have a map from, so L1T with norm 1 to C naught and lambda is a map for this. Observe that how does it follow? So look at the definition of this. So you see that lambda f is written as where f hat int dt. Now integration is a linear operation. Therefore you see that you have the following properties, namely f plus g gets mapped under lambda to f of hat n, which because of the definition of the hat operation is essentially this is the sequence, and that's equal to or if you want you one more little step you can write here for clarity. I can write this here. This is for the sequences. and similarly, one can prove this, that is, similarly, from fact that alpha f n hat, which is equal to it follows that linear map into C naught. This is an important step which we would use immediately. Now you know that it is not merely a map from a linear space into another linear space. It is a linear map from one normed linear space into another normed linear space, or from one Banach space into another Banach space. Lambda is Banach space C naught. So it is a map, a linear map from one Banach space into another Banach space, which we know at the outset is a into map. Okay. Now the natural question that you ask is that means C naught. or is it a linear map from L1T to C0? Now what one can easily prove that this is a boundary. Now note that which is equal to 1 by 2 pi now mod f hat which is nothing but norm of f1. Therefore, for every n, this is true for the norm of lambda is less than equal to. So it is a that's easy because norm of lambda equals to supremum of equal to 1 equal to 1 of lambda f. Okay, and we have already seen that this is bounded by, and this one, each one is bounded by 1, therefore this is less than or equal. Okay, so it's a bounded linear map. Now we observe the following. If T is a bounded linear map, T is 1 to 1 if and only if Tf Tx equal to 0 implies x equal to 0. Use this theorem. So what does it mean? So we prove that if and only if f is equal to 0, it's important. F need not be identically 0 because you know that in L1T, that means norm of F equal to this is the meaning of that. Okay, right? So F need not be identically equal to, it need not be need not be a 0 function, but it's 0 almost everywhere, so that integral, that norm of F1 is equal to 0. Okay, right. So we move step 2. Lambda is 1 to 2. This is the statement area. Step 2. Now we have seen that prove that equal to 0 implies first the other way around. If F is 0 in L1T, then naturally lambda F is equal to 0. That is something which you don't have to much worry about. Okay. So we start with C naught. Equal to 0 so what we have to show is that the following: if F is such that hat is equal to 0, is 0 element, then F is the 0 element of L1T. So we prove this by stages. Now F hat that is integral minus pi to pi equal to 0. So f is such that this property is true. Okay, and consequently, if P is a trigonometric polynomial, where complex numbers, then obviously Pt equal to, because each term is going to be 0, right? Because minus n. This is equal to 0. That is clear. Therefore, if P happens to be a trigonometric polynomial, then this is true. Now we claim now what we do is we try to approximate functions in CT. What is it? If f belonging to CT, then and epsilon positive, then there exists a trigonometric polynomial such P minus so every element in CT, every element, an element of CT is certainly in L1T. Okay, so every element of CT can be approximated by trigonometric polynomials as closely as you want. Okay, this result is something that we make use of. Okay, so we claim for every G belonging to CT. Okay, this is simple. So there exists a trigonometric polynomial PT epsilon. This is the previous result. We are just invoking that and writing down the result. Now we shall make the following computation. Now you see, we estimate this. We add and subtract PT plus dt. And you see that this is therefore this one. And this is 0. This is 0, which we have already seen, and plus modulus of this part is what? Minus pi to pi, and this epsilon times 2 pi times norm of F1, because F belongs to L1. Okay, and you see that this is true for arbitrary. This result is true for every epsilon positive. It follows that and that too for every G belonging to C. Now we leave CT because we have to work for L1T. Okay, so the characteristic function of A, where A is a measurable set of T, or minus infinity. Then we claim that A, where A is any measurable subset of T. Okay. So we make use of to the Lucian's theorem, and the bounded convergence principle. And from the corollary of we'll just, if G is complex valued Lucian's theorem is more general, but I am writing it particularly for this. Measurable function on T A contained in T is a measurable subset of T. T with measure of finite and G is equal to the characteristic function of A less than 1 which implies norm G is less than or equal to 1 and there exists a sequence Gn where Gn, that means they are continuous functions with compact support. Compact support norm of Gn less than or equal to 1 such that Gx equal to almost everywhere, or I will put it this way. This is almost everywhere. Which means except possibly on a set of zero. Now we use this one. So you see that integral over T F chi A let us make use of this. Then Okay. We'll come to that. So what do we do? Okay. So we use this result. Use this result as follows. Okay. Now you see that integral minus pi to pi this is equal to, by the previous theorem, it is minus pi to pi ft into limit n tending to infinity gnt. Now you know that gn is converges to g to chi a. Okay, therefore this is true, and that's equal to, here we use uniform boundedness theorem, says limit n tending to infinity and this, you know, now gn belongs to ct, which is equal to 0. Therefore this is equal to 0. So what do we have? So we have or equivalently okay. So what does this mean? This means that equal to 0. So this is the result that we make use of a measurable. This is true for every measurable subset. Okay, what next? The next thing is this. Now we make use of another result. So if f belongs to L1t and integral over a this is using one of the fundamental theorem that you have. So we use this theorem. Okay. Now using this result, every A belonging to the measurable class, and this implies equal to 0. So f is equal to 0 almost everywhere on T. So what does this mean? This means that equal to 0 in L1T. Zero belonging to C naught implies this is true. This is exactly what we wanted to do. Therefore, lambda is this one. Okay. So we have proved that lambda is a 1. Now the next step is third step. Not on. How to prove this? We do this by contradiction. Prove this assume onto since it is 1 to 1, lambda inverse exists as a linear map from C naught to L1. Okay, so the inverse exists and is bounded. So lambda inverse is a bounded linear map from C naught to L1T. This we infer from a general result that if we have both lambda linear, it's a bounded map, then you have this property. It's a bounded linear map and it is onto 1-to-1 and on-to, then lambda inverse exists as a bounded linear map from the range space C0 to L1T. So note that equal to I identity C. Lambda operates from L1T. Okay, because it operates from on vectors in L1T, carries it to C0, there's lambda inverse maps from there, and therefore you have, see, lambda inverse is this is our assumption. Okay, therefore this is identity on L1T that you are talking about. So you see that which term this acts on 1, so this is this, and this is less than or equal to but norm of lambda equal to 1, therefore norm of lambda inverse is greater than or equal to 1 upon equal to 1. That is for f belonging to L1T, norm of lambda f. Fy. This result is there. Now we shall work on this. Consider Fn to be defined as sigma and this belongs to Ct, okay, and Fn equal to dn by we have earlier designated this as dnt. Then dn belongs to L1T. That is clear because it's a finite sum that you are talking about. And This you need some computation. dn hat you calculate, you multiply by e to the power minus int or say imt, then compute fm. Okay, so that's easy to work out what it is. It turns out to be 1. That is because you want, you can simply work it out. Delta k. So we are making use of this. Okay, right? So whenever m is equal to k, you see you get 1, so you will get 1. Otherwise, you get 0 because of the orthogonality. Now you also see that if you take dn 1, okay, you take dn 1, this goes to infinity as infinity because it's a sort of increasing sequence that you encounter, and therefore no delta positive such that because this goes to infinity. So that's a contradiction. This is a contradiction. Okay. Therefore, this is what we got. Okay. So I conclude here. Thank you very much.